Okay, folks, what we're going to be doing now is determining what the pH of a solution is when you have a diprotic acid. Diprotic, dos, protic, protons, hydrogens, two hydrogens. All right, so for example, problem number 2 on the problem set. Problem number 2 says you've got a carbonic acid solution. And the carbonic acid solution, so I'm just reading from the paper. Now it says calculate the concentrations of HCO3, which is bicarbonate. And in carbonate, when you have a 0.025 molar solution of carbonic acid. Okay, so let's start out by writing out the reaction. Carbonic acid is a weak acid. It's one of the weak acids. We got to know what the strong acids are, so we'll know what the weak acids are. You have to know the strong acids. Okay, let's review that and put that down. HCl, strong. HBr, strong. HI, hello, hi, strong. HNO3, nitric, strong. H2SO4, sulfuric, strong. Strong like bull. 1, 2, 3, 4, 5, and HCl4 and HClO3. 1, 2, 3, 4, 5, 6, 7. All right. Chloric acid and perchloric acid, sulfuric acid, nitric acid. This is hydrochloric, hydrobromic, and hydroiodic. You might notice something that Cl, Br, and I are all in the same group. What about HF? I mean, H hydrofluoric acid, is that strong? No, it's not. It's not strong. The fluorine and the hydrogen have a relatively strong bond, and the hydrogen doesn't come off so easy. If we remember what strong acids are, it means they ionize 100%, 100% ionization. That means that every hydrogen will break off. Now, this one's a little interesting since there are 2 hydrogens. The first hydrogen that pops off here is a strong acid. So the H2SO4 is a strong acid, but the remaining species, HSO4 bisulfate, is a weak acid. So that one's kind of interesting. That one gets into what's called the, oh, you people are going to love that. That's a quadratic formula 1. Oh, shh, we'll talk about that. Right, scary. So let's get back into this. We have a weak acid, and how do you know it's weak? It's not strong. It wasn't one of the strong acids. It's a weak acid. Okay. So the weak acid breaks down and forms, or breaks down somewhat, not 100%, somewhat. Breaks down and forms hydrogen and the bicarbonate ion. Okay. Now, let's do an ice chart. It's weak, and therefore, we have to put the arrow going both directions there. If the arrow going one direction, it means it's strong. Both directions. Weak. Weak, like the Ukraine. You are weak. Ukraine is weak. Ukraine is not weak. Seinfeld. Okay. If you're a Seinfeld fan, you get it. Okay, so we have the initial concentration. Oh, now I forgot. Been a while. 0.025. 0.025. We start out with no hydrogen. Once this thing starts to break down, we don't have any at first. We have no hydrogen, but it will eventually break down and form hydrogen. So I start out with none of that. My change, we're going to lose this. We're going to gain this. We're going to gain that. And at equilibrium, 0.025 minus x. We're just adding our columns and the columns, plus x, x, plus x. Okay. So at equilibrium, with this breaking down into this, I'll have these concentrations. All right, with me so far? Now, this is a weak acid. And you thought that was a weak acid. That thing is like super weak. And the reason that is because this hydrogen that's connected to the carbonate doesn't really want to leave very much. It kind of wants to hang out with the carbonate, but you know, some of them go, I want to get out of here. And a few of them will leave, and therefore it's a weak acid, so not complete ionization. The remaining species of bicarbonate, that hydrogen is even more strongly connected to that carbonate ion. As that carbonate is like, hey, you know what, man? I gave you a hydrogen. I gave you one. I don't want to give you a second one. So it's even weaker, which means it doesn't want to break down even more. Okay. So this is a weak. This is a weak. So what this means is that this is going to further break down, but not very much. So if I write that reaction out, then we have some of this H coming off, leaving me with the carbonate ion. Now what happens is, I end up getting hydrogen from the first hydrogen coming off, and some little bit more hydrogen from the second hydrogen coming off. And I want to know the total amount of hydrogen. Well, I'm going to have to add those two numbers together. I'll have to add those together. So let's see. In the second reaction, the initial concentration of the HCO3 is going to be this X. Now, I don't know what that X is. I need to get that number so I can put it here. So that means I'm going to have to calculate it. Okay. This H goes, that's going here. I'm going to have some of that already hanging around because I made some H from the first H coming off in the first reaction. So there will be some H here. I don't know what that is. I'm going to have to figure that out too. Okay, so what I should do here, and then carbonate is going to be unknown. At this point, I haven't made up here, at this reaction, I've made no carbonate. There's no carbonate here. Here I'll make carbonate, so when I go in the second reaction, now I'll start out with none of this to begin with, because I haven't made any yet. So that gets a 0, but I need to know what those values are so I can do the initial concentration here in my second ice chart. You're going to need 2 ice charts. 2 hydrogens coming off, 2 ice charts. Okay, so I need to do a calculation here. Now remember our K calculations are equal to the products and their concentrations over the reactants. So this product, H, has a concentration of X. So I'm just going to take the square bracket out and just jump right into that and put the X there. X. This is X. So that's X. Over here, 0.025 minus X. Okay, that means I should have been given in this problem a K value for the carbonic acid, or I am big trouble. Let's see. I think I was. I believe I was. The Ka for carbonic acid is 4.2 times 10 to the negative 7th. 4.2 times 10 to the negative 7th. All right, so I solve for X here. If I go ahead and solve for X, I am going to get rid of this X. It is small. The rule of 100 says that if you take the initial concentration, 0.025, and you divide it by the K value, which is really tiny, and you get a number greater than 100, we can ignore it. We're going to ignore it. Because I know that that divided by that's going to give me a very small number. I'm sorry, very large number, because this is a very small number here, so I'll get a very large number, greater than 100, greater than 1,000 even. So I'm going to ignore that X and get rid of it. It's so small, it's insignificant, and doesn't matter. I know that hurts its feelings. All right, gone. Oh, that makes the math so much easier. Cross multiply. Take the square root. Okay, so in other words, we're going to take this like this. 4.2 times 10 to the negative 7. 0.025 equals X squared. All right, solve for X. So take the square root of this product, and we will get X. Whew. For these two species from the breakdown of the carbonic acid. All right, X comes out to be, and I did this out earlier. Let's see. So we'll speed things up here. Check it, though. Make sure you check me. Make like a hockey player. Check me. Check. X comes out to be 1.02 times 10 to the negative 4th. So X is 1.02 times 10 to the negative 4th. And that guys, we're all done with the problem, right? I don't think so. No, because we need, now take that X value that we now know is for this bicarbonate ion concentration when it breaks down. And we also know that we have some hydrogen already created. So I'm going to take those X values, and in the second reaction, the second breakdown, the second hydrogen coming off, I start out with that amount, 0.02. So you could actually, I mean, if you want to write it out like that, or you can put 0.0000102. 1, 2, 3, 4. That's my initial concentration, not very much. You know, this, again, this doesn't break down very much. So I don't end up getting very much of these species out of it. And this one's going to break down even less. Okay, so I also have hydrogen. I have some hydrogen to start out with. Some hydrogen came off from the first dissociation, and that is 0.000102. All right. What happens? Well, I'm going to lose some of this. Some of that breaks down, so I lose some of it, negative X. I will gain some more of this. I'll gain more hydrogen. So this will be positive X, and I'm going to make some carbonate ion, positive X. I'm trying to keep within the screen here, so if I go ahead and do this out, I get 0.000102 minus X. This is 0.000102 plus X and X. Okay, now I'm running out of room down here, so what I'm going to do at this point, I'm going to erase this. I'm done with this. Get rid of you, get rid of you. I'll leave the original equation up there in case we need to work with it. We'll leave this, move this. All right, we're done with you, move you, and we're done with the math. So we'll move the math. Okay, so let's go ahead and put these numbers into a K equation, so we can figure out what the X's are here. All right. Okay, now I'm going to need K for the bicarbonate, weak acid. And that was given in the problem as well, or darn well better than. Oh, good. Back in my day, we had to memorize all the K values for every single acid. No, actually we didn't. That's why I'm looking it up. Okay, 4.8 times 10 to the negative 11th. So the K value is 4.8 times 10 to the negative 11th for that bicarbonate, that HCO3 negative acid, weak acid, very weak. If you remember the K values tell you how much it wants to dissociate. That does not want to break down very much. It's a very, very small K value. Okay, so we have the two species, the two products on the right. So H is 0.000102 plus X. Okay, and CO3 is X. Okay, that's all over the reactant, 0.000102 minus X. This is going to take forever. I don't want to do it anymore. Now, well, it's a piece of cake. Look what happens. Remember, these X's really small. If you take the initial concentration that we had, 0.025, and you divide it by the K values, that's a tiny K value. You're going to get a huge number. So that means these X's are really, really small and insignificant. So that can go bye-bye. That can go bye-bye. You see it, don't you? You see it. Yes, you do. Yes, you do. Gone. Gone. They're going to cancel. You have the same thing on the top and the bottom. So this math was easy. We just solved for X. 4.8 times 10 to the negative 11 is equal to actually the K value. Wait. What was the original question? What were we trying to figure out? I think what we're trying to figure out is how much of each species that we have, each part that we have, when we finally have established the equilibriums. All right, okay, we'll just verify that. Let's see, this is question number 2. Yeah, calculate the H. Okay, calculate the total amount of H. Now, the total amount of H is, okay, now X for the second reaction is equal to that. So we're going to take this number and add to it that. Negative 11? Negative 11? That's 0.0000000000. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. That is that. We now have to add that to this. You know what? This is completely insignificant. It's going to end up being way out here, so it doesn't change anything. So that means that the concentration of the hydrogen at equilibrium is that. Because that's it. If you want to, if it makes you feel good about yourself and better about yourself, and we want you to feel good about yourself, then go ahead and add that in. Yeah, add that in. Go ahead. Do it. Do it. Do it. You won't. But it's so small, it's insignificant, it doesn't change anything. So I'm just going to call AH as being equal to that value. Okay. That also means that the carbonate ion is X at equilibrium, which is that value. So this is the amount of carbonate at equilibrium. All right, so we've got the amount of H, we've got the amount of carbonate, the amount of HCO3 is going to be equal to 0.000102 minus this really tiny number. And again, trying to show you up here how small and insignificant it is, it doesn't change anything. If I can go ahead, if I want to subtract this from this, I can do it, but it's not going to change it. So this is the amount of bicarbonate that I have at equilibrium. Again, if you want to go ahead and subtract the X and put that in there, go ahead and do it. Feel good about yourself. But it's not going to change anything. It's so insignificant. It's so far beyond the significance, it doesn't matter. And all right, I think, yeah, that's it. That's it. We've wrapped that problem up. Yeah, we've made it like a gift.